my talk's going to be heavy on data. And so we're not just imagining things, Jeff. Okay, I'm going to take you all on a tour of plumes in the solar system, which is also sort of a history of my career in an odd way. I'll start by talking about not cryovolcanism, which are the solar-driven jets on Mars, because I want to contrast their properties with clear cryovolcanism, the plumes coming from Enceladus and possibly Europa. And then I'm going to pose the question of what is driving Triton's plumes and touch on Pluto. So this is a HiRISE image. HiRISE is the camera on the Mars Reconnaissance Orbiter. This image is about 6 kilometers wide. The color band in the middle is about 1 kilometer wide. And this is an area on the South Polar cap, near the South Polar cap. This particular one is at about minus 85 degrees south latitude. And you'll notice immediately all these little dark fans on the surface. These fans are on the surface of a seasonal CO2 ice cap. And we have a story for the fan formation. I think, again, I'm going to claim it's more than a fairy tale. And it goes as follows. In the winter, you get a layer of CO2 ice deposited either from direct condensation or by snowfall. And over the course of the winter, it anneals into an impermeable layer, 0.5 meter to 1 meter thick. When the sun comes up, you've got sunlight penetrating a somewhat translucent layer and warming the ground below. Gas gets, the ice starts to sublimate from the bottom. Gas gets trapped and pressurized, and wherever you can find a weak spot, eventually it's going to break through and escape. And it entrains surface material, which then comes out, gets carried by the local winds, and gets deposited on the surface in these fans that we see in the images. We've done a number of studies with HiRISE to substantiate that model or look to see if it's not right. And so here's one of our gazillion images. You can see the fans. It's early in the Martian spring. Here's a blow up of this area is shown here. These fans erode very Martian kinds of features. We call them spiders or RNA-formed terrain. This particular one is about 0.5 kilometer in diameter, so these are large structures, but they're not deep. These are channels that are carved into the surface. It's not carved into the ice, it's carved into the surface. They're 1 meter or 2 deep, and the channels can be up to, I don't know, 5 or 10 meters wide. Now the interesting thing, I don't have a 3D, but this is draped over a mound, and these things like to drape over mounds. And so that means that the deep part in the center is actually uphill. And so that sort of erosion, of course, is consistent with confined gas being what's carrying the particles out. Okay, so what we've done is a lot of modeling with some commercial code that's available called Phoenix. And you can look at your observables, things like the fan length, and you can derive things like the fan height. You can see what the local wind speed effect might be. The business about the pressure of the ambient atmosphere comes into play on Mars. That limits the heights of the plumes. Just to show you a couple of examples. So with this code, we're able to study these parameters for these jets. And some of the insights from doing that is that the large particles do decouple from the gas. The small ones tend to stay entrained and actually affect the plume itself. And then the particle sizes will separate out differently depending on the wind because the small ones will go further. They just get carried along. We can derive gas exit velocities and mass flux. And the vent size is actually limited by the resolution of the HiRISE images to something less than 1 meter, probably quite a bit less. We have yet to actually detect a plume. I have to put that out there. But there's a good reason for that, which is that the derived lifetime of these things are something between 10 minutes and 2 hours, and we can only do stereo on adjacent orbits, which are separated by 2 hours, so we'd have to be incredibly lucky to catch one of these in action. So just to wrap up the Mars story, this is what it looks like through the course of a Martian spring. In the beginning, you've got that 0.5 meter to 1 meter of CO2 ice, and then fans start popping out. This part on here is a slope, a rather steep slope, so you can see the fans tend to go downhill, whereas over here they're more oriented by the wind direction, and particles actually fall onto the surface and then sink in. So there's all kinds of cool stuff. Polygonal cracks form. It's really, really fun. Okay, so I'm not going to talk about Triton just yet, but I will point out that there's a lot of sort of superficial similarities. You've got your dark fans. They appear to be oriented in a direction that was probably influenced by the wind. Here's one of the geysers erupting right here, going up 8 kilometers, spreading out actually all the way. The material is coming all the way out to about there. The other ones are down around here, a little harder to see. And it was a solar-driven geyser model at Triton that actually inspired the models for Mars. Okay, Enceladus. I want to say that it was the magnetometer team that should get the credit for finding the plume. When I say plume, I'm referring to the bulk stuff coming out, whereas the jets being the individual streams of particles and gas. Of course, they're coming from these fissures across the South Pole we call tiger stripes. As a member of the Cassini-UVIS team, we wrote so many papers that said our data is consistent with a body of liquid under the icy crust. And so everyone was so happy to not have to write those words is consistent with, once the gravity folks had established that there really was a body of liquid under the South Pole. And then from the images and the libration data, we could say it was global, and the latest results on the shape suggest that the crust is 20 kilometers thick and quite a bit thinner at the South Pole. So here are those hot spots along the tiger stripes. Here's the location of the particle jets. Here's up here's the UVIS data. The way we study the plume is to watch a star go behind the plume, and so here are the collimated streams of gas that we detected. The larger particles, so as David was saying, the smallest ones escape, form the E-ring, but the larger ones fall back onto the surface, and this is a model of their trajectories, and you can see it in Paul Schenk's color maps that it actually, this fallout actually does affect the distinctive color of the surface. Okay, so just to spit out a whole bunch of data, or things derived from data, we know what the composition of the plume is. It's primarily water that comes from the UVIS spectra. The trace amounts of H2, ammonia, CO2, and methane come from the ion neutral spectrometer on board Cassini. One of the nice things about having your body helpfully erupting stuff into space is it means you can fly your spacecraft through it. And so I think we had a total of 23 or 24 Enceladus flybys in the Cassini mission, and a number of those went through the plume. The velocity of the gas has come up a couple of times. I want to say that these numbers came from me, but they don't come from our data. What you get from the UVIS data is the ratio of the velocity in the collimated gas streams to the thermal bulk velocity. And this number of 450 simply corresponds to the thermal velocity that you would get for a temperature of 170 K. So, but that is if you take that number, then you can derive from our ratio the 1 kilometer per second, or possibly higher. And I'll just point out escape velocity is 230 meters per second. So the gas is definitely escaping. The mass flux in the big plume has stayed very constant over the 12 years of the Cassini mission. On the other hand, in the jets, we do see the column density vary. And so that goes nicely with the particle brightness, the fact that the brightness of the plume is a function of where Enceladus is in its orbit. And so what we see is that the bulk gas coming out is constant, but the jets do tend to have more gas as you get closer to 180. The particles have two compositions. The pure ice grains are the tiny ones that likely condense in the throat and get ejected all the way to form the E-ring. The salt-rich particles are the ones that tend to fall back onto the surface with something less than escape velocity and a height something less than 1,500 kilometers. And then Ingersoll and Ewald derived 50 kilograms per second for the particulate mass flux from the imaging data. So the cool thing about studying Enceladus plume is it reveals all sorts of stuff below the surface. And we can also insist that any models be tested against these plume observables. And your model should work if it predicts what we see in the data. So diurnal modulation of the brightness really implicated tidal energy, which we all thought was the case, but it was nice to get an indicator in the data. I've talked about gas and jets, some escaping, some not. The composition was revealed to be, there's salts in the particles, so we know that the liquid is salty water. The presence of silica nanoparticles, which were discovered by the dust analyzer on Cassini, implicates hydrothermal vents at the bottom of the liquid layer. Methane seen in the plume is evidence for serpentinization. That could provide the H2 detected, and of course, that's all very exciting for people interested in habitability. Some cautionary words on Europa. So I actually also think that they're likely to be real. So the discovery was reported by Roth et al. In 2014 of seeing surplus emission at the limb in Lyman alpha and 1304 angstroms. And so that was interpreted, of course, to be coming from water vapor. And you also do have emission from the bound oxygen atmosphere that you have to disentangle, which I think they did convincingly well. But of 20, a total of 20 emission observations, only one has showed this enhanced emission at the limb. So they seem to be transient. And another technique also sort of comes to the same conclusion, which is observing the plume at the limb. So that little teeny dark bump there is a place where Jupiter's light is being blocked by this putative plume. And so this observation has been carried out for 12 transits of Europa in front of Jupiter, and in 4 of those, they detected a little teeny bump on the limb. One of the fun things about the fact that this data is in the ultraviolet is that you can make really direct comparisons between the HST UV data and the Cassini UV data for Enceladus. And so looking at a couple of the techniques, emission features, well, that works really well for Europa because the electron energy is greater. It's not so great at Enceladus, although I will point out in this Enceladus spectrum, we did see this little teeny bump here from 1304. So it's not impossible, but it doesn't really yield very exciting results. Absorption of the signal, you can imagine using Jupiter as your source of light or Saturn as your source of light, depending. And I'm going to give you a spoiler conclusion, which is that Europa's plumes are really quite different than Enceladus, and I'll show you why. So we tried to do this observation of Enceladus in transit across Saturn, knowing that there was a big water vapor plume. And so we parked the UVIS slit on Saturn and let Enceladus come walking across it. And then we repositioned and let it happen again. And we did that 3 times. And the bottom line from all of that is that the noise was greater than the signal. So there was no detection. And so this is my picture of the plume, and you could see, maybe you could see a little bit of darkness there, but it's not real. Or it's not believable statistically, I guess I should say. But if we had used, if Enceladus's plume had been as what the column density reported for sparks, we would have seen that. And so to just list this all, first of all, you've got your duty cycle. The Enceladus eruption is ongoing. It is modulated diurnally, but it has not stopped in 12 years, probably not in the last 100 years. The column density, whereas Europa eruptions, so the geometry for these transits is roughly the same. You're looking from Earth, and so you're not seeing a wide spread of longitudes. So clearly, the duty cycle is different, and sparks derive 17%. The column density, you can see the difference in the numbers here, 1.5 times 10 to the 16th versus 10 to the 17th per centimeter squared. So an order of magnitude. Just the fact that Enceladus is so little and Europa is so big means that having plume scale lengths about the same, that the velocity must be much higher. And then the total eruption mass is a difference of 2 orders of magnitude. So when you put all of this on a page, the way I have, you have to conclude that there's some big differences. Maybe tidal energy is the driving force, but still the plumbing, the energetics, the mechanics, whatever, absolutely are creating different beasts. And it's dangerous to extrapolate from Enceladus to Europa. Okay, Triton, my personal favorite place in the whole solar system, just to put that out there. It's Neptune's large moon. It has a nitrogen atmosphere and vapor pressure equilibrium with surface ice. Voyager flew by. So here's the subsolar latitude, and you can see the centuries down here. In 1989, when Voyager flew by, it was extreme spring. And the subsolar latitude was further south than it had been since sometime in the 1300s. This is because of so Neptune is tilted, it has an obliquity, but then Triton's orbit is also inclined. So the two have this kind of beat frequency with each other that means it only repeats about every 640 years or so. Triton has a very young surface, geologically speaking, and this is work that Paul Schenck and Kevin Zonley did in 2007. Less than 10 million years is almost like nothing. If Triton was captured 4 billion years ago, that signature should have been long ago lost with more recent impact. So that's interesting. And then Nimmo and Spencer published a paper. It was actually in the Pluto prediction special issue, which I get a kick out of. But anyway, they did the calculations to show that obliquity tides could supply the necessary energy for surface yielding that would erase craters, and they derived a convecting ice shell 100 to 300 kilometers thick, and you can get this liquid layer warm enough if you have some ammonia to still be liquid. Okay, so coming back to the plumes, there were 4 active plumes. There may have been others, but those are the ones we're certain of. They went up 8 kilometers. Here's the one that's easy to see again. You can see the little stem and then the particles going off this way. We also saw it in these 3 images, so you could really be certain it was poking up above the surface. We get a mass flux derived from the opacity of the plume. The gas flux is a little iffier because it's model dependent. 120 fans for certain on the surface. We assume that they're probably from no longer active plumes. These fans were only seen in the southern hemisphere. However, a big chunk of the northern hemisphere was in polar night. So you can't just say they're not in the north. There's a huge chunk of territory we couldn't see. Anyway, you can derive a lifetime of about 3 Earth years if you assume that they don't survive seasonal volatile transport. So the solar-driven model, these are the basic tenets, that you will get a seasonal layer of nitrogen ice, that you can form a solid-state greenhouse in or below that seasonal nitrogen layer, and there's plenty of energy just below that impermeable layer to get a temperature rise. You only need 4K, and then you get a 10x increase in vapor pressure. And so, of course, you've now got pressurized gas. It's going to want to escape. And, you know, if you do the calculations, you can get up to 8 kilometers at 180 meters per second. The circumstantial evidence for this was that we saw the plumes in the southern hemisphere, and the fans are all in the southern hemisphere. There are challenges with this model. You have to have this giant specialized gas collection area, and you have to be able to capture enough energy at the top to get your 4K rise in temperature. And so it's a little tricky, but it's not impossible. And that model has survived till now. But it turns out that Randy Kirk and others also considered an endogenic model in 1995, where they had water ice with ammonia hydrate or water with clathrate hydrates. And so here were some of the requirements for that to work in terms of vent size and exit velocities. They did not pursue this because the solar-driven model was plausible and it was consistent with circumstantial evidence. So, you know, let's just go with the solar-driven. But some things have changed. The estimate of the surface age, the obliquity tides as energy source, and we have Enceladus, right? So now we have an example, which we did not have back in 1995, of regional activity confined geographically. Vent sizes and exit velocities are actually similar to what we derive for Enceladus. And so I'm campaigning for us to reconsider an endogenic source for Triton's plumes. So I put this table together to compare Mars and Triton and Enceladus, and I'm not going to read all the numbers, but I just want to point out down here in the mass flux for vapor and particulates that the numbers at Triton are much more like the numbers at Enceladus and much less like the numbers at Mars. What about Pluto? Well, I was very excited prior to New Horizons about what Pluto could tell us, but it turns out that other than Sputnik Planitia, it's, you know, kind of got this old surface, and who knows if there's internal heat? Probably somebody does, but not me. There's no obliquity tides. It doesn't appear that there's a seasonal polar cap. So it's late northern spring on Pluto. There should have been remnants of a limited north polar cap. There should be a large south polar cap forming. But given that Sputnik Planitia is this major cold trap for nitrogen, it's at the most stable latitude, you know, it's bright, it's a place nitrogen's going to want to go and stay. It's kind of wiping us out. So if we had seen fans on a seasonal polar cap at Pluto, we would have said, yes, Triton and Pluto's jets are solar-driven. If we had seen seasonal polar caps but no fans, or plumes but not associated with seasonal ice, we could have said Triton's plumes are endogenic, but darn that Sputnik Planitia, even though it's in the shape of a heart, it ruined my test. So just to conclude with this last slide, the places. So here's my score sheet. Mars, solar-driven, no doubt about it. Europa, probable, but not like Enceladus. Enceladus, definitely. Triton, a really obvious test is just go fly another spacecraft by Triton. You have to do it pretty soon, you know, before the South Pole is in polar night. But if the geysers are still erupting, then the source is probably endogenic. And if not, they were probably solar driven. So it's a very easy question to answer as long as we get there, you know, relatively soon. And Pluto, of course, we've heard no plumes, but other cryovolcanic processes may be active. So what I come away with is that we have this incredible, wonderful variety in our solar system. Thank you. Lots of hands.
So one of the things about the Europa plumes that concerns me is why didn't Galileo see them? And I hadn't really processed what you pointed out, that they would be 2 orders of magnitude greater mass flux, which sort of made me think they would have been easier for Galileo to see.
If they were going off.
Yeah, but if they go off 17% of the time, and Galileo was there for years, how the heck did we miss them?
Not lucky.
Wow. Okay.
Primarily because Galileo couldn't expend the resources to look at high phase. We were, with the limited downlink, we could only do what mapping we could do, which was minuscule. So we just didn't get any high phase. And even at Enceladus, you still need the high phase observations or the solar eclipses or whatever to see the plumes. You don't see it in full light.
You don't see them in transit.
At low phase.
Even though we know they're there.
Yeah.
I actually am the one guilty of making that contribution to the Kirk et al. Chapter. And I have to say, out of all the wild and crazy things I've proposed in my life, I felt more sheepish about that endogenic model, more insecure than just about any wild and crazy thing I presented. But it was for the reasons that you mentioned.
Yeah.
And now those reasons are alleviated. I'm happy to move over. I kind of hope I can sit by your side because I like the idea.
Okay.
Well, so one of the things we know about the endogenic plumes on Enceladus is that they're closely associated with tectonic features.
Yes.
And occur in nice lines, which is
Yes.
not necessarily true of the Triton plumes. And that's one of the things that makes me skeptical. I mean, there are tectonic features that continue down into the south polar terrain of Triton, but they don't seem to really be associated with the plumes as far as I know. So anyway, that's just something that gives me pause about
valid.
that.
That's a valid concern. Yep.
I'd add that quite a lot of the tectonics on Triton, you can kind of see going under that polar cap and getting more and more submerged the deeper you go into the cap. And so I wonder if there are features like that that are buried underneath that we may or may not see. They wouldn't look, I don't think, all that much like Enceladus sulci, admittedly, but if there was something fairly shallow, probably with less topography than Enceladus, it could be completely concealed.
David?
David and me.
You used the word drive. The Triton plumes were driven by their source conditions to 8 kilometers altitude. How did? I guess I'm wondering. When you say drive, that to me means like momentum driven as opposed to buoyant, because they obviously go up and then go.
Yeah,
in
they
some
are.
direction.
Yeah. So I'm probably not making a precise choice of words
But
on
I mean,
that.
that says something about the energy or the temperature at which
When
they
you
came out.
when you
or whether
model
they're
exactly
buoyant.
when you model the energy available for going from 38 Kelvin to 42 Kelvin and put that energy into your gas and then let it escape, but there's a lot of physics that I'm glossing over, and I would really direct you to the Kirk et al. Paper in 1995. Because they do go into, there's so many caveats and things about their model that I can't do justice to.
I just wanted to get on the soapbox here and discourage people from referring to this as a polar cap on Triton. Warren Spencer wrote a really nice article poo-pooing the idea, and you see impact craters going down to low southern latitudes and the continuing geologic structures. There may be nitrogen deposits, but they don't form a polar cap in the sense that we have on the Earth or Mars. So,
yeah, let me also point out that we actually have no idea what was on the surface at the time of the Voyager flyby, because we had no near-infrared spectrometer. We had no means of getting composition. And so, you know, all you have is that sort of scraggly edge that looks like it could be the edge of some sort of an ice, like not even necessarily nitrogen. It could be methane or something. And so,
well,
yeah,
there's certainly ices of different composition. We just can't pinpoint, like on Pluto, where they are distributed. They're just broad brush hemispheric scale differences.
I just have a question about Triton itself with the flyby. How well is then the ice shell thickness constrained by that data? Because you said something like 100 to 200 kilometers.
Yeah, no, that's totally from a model, derived from a model. It's not constrained by Voyager data.
Oh, okay.
Yeah.
So yeah, because then my question though is just like with such a thick shell, how would you get liquid, you know, that close to the surface to provide?
Right. And I am in campaigning for plumes to be endogenic, I am saying we actually don't know what they are, but let's not rule this idea out. And I will point out that at Enceladus, we also initially thought, how in the world is stuff getting through 100 kilometers of ice, and then come to find out it's only 20 kilometers, and maybe at the South Pole it's only 1. So, you know, you start off from these positions of not knowing much and having to rely on models. But then as you get more data, your models get better. And so I think the same thing is going to happen with Triton.
Just a very quick response to that.
When
When you speak to Francis now, he pulls back a bit from the up to 200 or 300 kilometers, and I think he gives numbers like 30 to 150. There's a great uncertainty from the modeling. And so it's all models, it's not really data constrained, so take it all with a pinch of salt there.
Yeah. Phil, I guess.
Yeah, I'll just add to that. It's of course you could have an IO-like situation where you have something more like ammonia water cryovolcanism that isn't giving you a direct plume, but is mobilizing what we know from Earth-based spectra is on the surface of Triton, which is our methane and nitrogen ices like on Pluto.
Mm-hmm.